We talk about the cloud as if it floats above us, a weightless, invisible network of pure information. But every email you send and every photo you upload requires the physical manipulation of atoms inside heavy industrial machinery. For 70 years, engineers have waged a continuous war against chemical decay and the hard limits of material science. To see where human memory is going, we have to look at the violent metallurgy required to hold on to it. There is no virtual space. The information age relies entirely on heavy engineering overpowering natural entropy. In the 1950s, data storage looked like heavy industry. The IBM 305 RAMAC was a massive machine, dwarfing the engineers who built it. It held memory by coating giant aluminum platters with iron oxide. They were painting metal with literal rust. To read magnetic charges, those 24-inch disks spun at 1200 RPM. This created intense centrifugal forces, pushing the metal to structural limits. If a disk warped, the read head would crash, physically shredding the data. Software couldn't fix this. Metallurgists had to invent entirely new magnesium-aluminum alloys, designed specifically to force the platters to remain flat under extreme stress. Early computing was a brute force struggle against the structural integrity of heavy metals. By the 1990s, the magnetic grains holding our data were shrinking. If engineers made them any smaller, the metal became unstable and simply forgot the information. The solution abandoned classical mechanics for quantum physics. Giant Magnetoresistance stacks alternating sheets of magnetic and non-magnetic materials at the atomic level. Instead of standard magnetic fields, this reads data by measuring the quantum spin of individual electrons. Reading these quantum signatures demands terrifying physical precision. The sensor must hover incredibly close to a blurred, rapidly moving mirror finish. At 5 nanometers of clearance, it is equivalent to flying a commercial Boeing 747 1 millimeter off the ground at Mach 800. Bypassing the limits of standard metal meant turning the hard drive into a quantum instrument where a single microscopic speck of dust causes total destruction. To escape the inevitable mechanical failure of moving parts, the industry moved to solid-state drives. We traded heavy metal for pristine, brittle silicon wafers. Looking at the structure of a floating-gate transistor, the drive captures data by locking individual electrons inside a microscopic silicon cage. To get the electrons inside, high voltage violently pushes them through a thin oxide barrier in a process called Fowler-Nordheim Tunneling. Every time a file is saved, this physically wears down and cracks the oxide layer. Modern solid-state memory consumes itself. We destroy the silicon to keep the information. Because metal rusts and silicon degrades with use, all the data humanity currently generates has a strict physical expiration date. To solve this, researchers are moving away from magnetism and volatile electricity. They are turning to optics. In Project Silica, femtosecond lasers fire incredibly rapid pulses into clear borosilicate glass. The laser etches microscopic, three-dimensional pixels, called voxels, deep inside the material. This glass is chemically passive. It can be boiled, baked, or scoured without losing a single bite, halting the entropy of material decay. The cloud requires immense physical infrastructure. It relies on millions of tons of steel, power, and cooling to simply exist. We have spent decades wrestling with spinning iron oxide, burning through silicon wafers, and now carving eternal data into glass. Every time you save a file, you manipulate physical atoms. You are participating in a 70-year legacy of metallurgical warfare.